a very important but a new topic. So far up to the last class, we have seen the chemical bonding and we have completed chemical bonding, how the atoms are trying to be together and what makes the binding between the atoms and why the atoms are trying to be together. All these things we have seen in the last class. So first we started with the periodic table, the periodic trend. First, we started with the periodic trend and the periodic table, how the elements are arranged in a systematic manner in a table, and then how certain important characteristics of the elements change when you move along the period and when you move down the group, and all these things we have seen. And then in the second chapter, we concentrated on the tendency of the atoms trying to be together, why atoms combine to form a molecule. All these things we have seen, and we have seen the ionic bond, covalent bond, and coordinate covalent bond, and their characteristics, and the important properties of ionic compounds, covalent compounds, coordinate covalent compounds. All these things we have seen. Today, we are going to start the S block elements. Now, in the periodic table, when the outermost electronic configuration is NS1 or NS2, we are able to find the S block elements. The first column or the first group of S block elements is called alkali metals, and the second group is called alkaline earth metals. Alkali metals are lithium, sodium, potassium, rubidium, cesium, and francium. Alkaline earth metals are beryllium, magnesium, calcium, strontium, barium, radium. And hydrogen is at the top, actually, which is not considered one of the alkali metals. See, the metallic character itself is the tendency to lose the electron. That is the metallic character. Non-metallic character is the tendency to attract an electron, to have an affinity towards the electron. That is electronegative character. But in the higher secondary itself, you might have studied the general characteristics of alkali metals and the general characteristics of alkaline earth metals. As these things you have already known, these fundamental pieces of information are taken away from the undergraduate syllabus. So we directly start from the anomalous behavior of lithium. Even though lithium is also a part of alkali metals, it has very peculiar behavior, and it is found to be odd among the alkali metals. So the lithium, sodium, potassium, rubidium, cesium, all are alkali metals, and also all are having identical outermost electronic configuration NS1. Even then, lithium shows anomalous behavior. And this anomalous behavior is due to the size and the charge. So lithium is also with a unit positive charge if it loses one electron. Sodium also with unit positive charge. All the alkali metals are with a unit positive charge when they are losing the NS1 electron. But when you compare the sizes of all the elements, lithium is found to be the smallest among the alkali metals. And because of the smallest size, its charge density is high. As the charge density is high, it has the highest polarizing power. In the last class itself, we have seen what is polarizing power and what is polarizability. Polarizing power means it is the capacity of the cation to distort to de-shape the electronic cloud around the anion. How easily the electronic cloud around an anion is disturbed is called the polarizability. So polarizability is more found for bigger ions, but polarizing power is more found in the ions of a smaller size. So the first anomalous behavior of lithium is it is the hardest metal among the alkali one, which has the high melting point and the boiling point. And the second important behavior is it is very least reactive, except with the hydrogen. It reacts with the hydrogen, but in general, it is least reactive. Suppose if you put a metal piece in water, you might have not seen this in your schools, how the sodium metal reacts with water. If you take a small piece of sodium metal, the sodium metal, even though it is called metal, it is very rubbery. You can simply cut the metal using a blade. There's something, a rubber-like structure. But the sodium metal is always kept immersed in kerosene. The reason is sodium is highly reactive with water. Sodium can easily combine with the water to form sodium hydroxide, and the hydrogen will be liberated. See, in our classes, we have this experiment, a sodium fusion extract, where a small piece of sodium is kept in a fusion tube, and the substance is heated to redness and then plunged immediately into water to make a sodium fusion extract. During that experiment, so if at all a small piece of sodium is thrown into the water, you can see the vigorous reaction. Sodium will immediately form sodium hydroxide and liberate hydrogen. The liberated hydrogen is impure, so the impure hydrogen will catch fire. So that is called the decomposition of water. Water is decomposed. The decomposition of water, the reaction is slow with lithium, but fast with the sodium. Will generate a flame with the potassium, but it is a highly explosion reaction with the rubidium and cesium. But in general, when you compare the reactivity of all these metals, lithium is found to be the least reactive. And the third behavior is lithium alone will combine with nitrogen. Normally, nitrogen is almost an inert gas. Even though it is not a noble gas, nitrogen molecule is inert because nitrogen itself has a half-filled electronic configuration. In nitrogen molecule, the p orbitals are completely filled. So the molecular orbitals are not half-filled or partially filled. So they attain stability. That is why nitrogen is almost an inert gas. But this inert gas shows reactivity with lithium. Lithium alone is capable of forming lithium 3N, that is lithium nitride. And also in the previous point itself, we have seen that lithium shows least reactivity except with hydrogen, which means that lithium can combine with hydrogen to form lithium hydride. Only lithium hydride is stable, whereas the sodium hydride or potassium hydride or rubidium cesium hydrides are not stable because the delta H formation, enthalpy of a formation is large negative in the case of lithium hydride. But the hydride formed is stable, but other metals also form hydride. But another anomalous behavior is lithium hydride reaction takes place at 700 to 800 degrees centigrade, whereas other metals are able to combine even though the hydride is unstable They are able to combine at a temperature 350 to 430 degrees centigrade. So even though lithium is not much reactive with the hydrogen, its hydride is more stable. It is not much reactive, but hydride is more stable. So for example, this is something like Indian marriage. In India, even though they do not like each other, the reactivity is very less. But if they are getting married, they will remain unseparated for quite a long time. The pair is stable. So the fifth point, lithium, when it reacts with bromine, the reaction is very slow. But all other metals show very fast reaction. And also lithium can combine with oxygen to form lithium oxide. Whereas other metals form peroxides, sometimes dioxides. See, sodium peroxide is available. Hydrogen peroxide is available, but hydrogen is not taken into the list of the alkali metals, but sodium peroxide is available. Potassium dioxide is available. Rubidium dioxide is a cesium dioxide. They are all available, but lithium alone forms oxide. See, oxides, there are almost 3 types: oxo, peroxo, superoxo. Oxo, peroxo, superoxo. I will explain that at a later stage. And also lithium hydroxide, when it is heated to red hot condition, you can see the decomposition of lithium hydroxide to form lithium oxide. The lithium oxide is showing least solubility in water. But other hydroxides, they do not decompose. They are all very stable. You cannot decompose sodium hydroxide or potassium hydroxide. And also these hydroxides are highly soluble in water. And another thing, lithium oxide solubility is also very less. Hydroxide also very less. Solubility also very less for lithium oxide. And the ninth property, lithium hydroxide is a very weak base. Lithium hydroxide is a very weak base. And also its solubility is almost equal to that of the calcium hydroxide. And also lithium salts formed with fluorine, phosphate, oxalate, and carbonate, they are all sparingly soluble in water. But the same salts of sodium and potassium are highly soluble. Sodium fluoride or potassium fluoride, sodium phosphate or potassium phosphate, sodium oxalate or potassium oxalate, sodium carbonate or potassium carbonate. These are all highly soluble. But lithium fluoride, lithium phosphate, lithium oxalate, lithium carbonate are sparingly soluble. If you compare the solubility of these salts, they are almost equal to that of magnesium salts. And also, these salts of lithium are sparingly soluble in water, whereas the same salts of the other alkali metals are highly soluble in water. But these salts are soluble in alcohol, whereas other salts are insoluble in alcohol. See, lithium chloride, lithium nitrate are soluble in alcohol. I request the students to be to wait for some time. I'll be back now. So the lithium chloride, lithium nitrate are alcohol soluble, but whereas the chlorides and the nitrates of other alkali metals are insoluble in alcohol. Similarly, lithium bromide and lithium iodide are soluble in organic solvents. But sodium and potassium salts of bromine and iodine are insoluble in organic solvents. And the 13th point is aqueous solution, the crystallization. Look here, when you are preparing an aqueous solution, that is a solution with water. When the concentration of the aqueous solution is found to be a little bit higher, we call it a saturated solution or supersaturated solution. Normally, the nature of the saturated solution is to crystallize out the dissolved salts. And the dissolved salts will crystallize out in the form of hydrated salts. Look here, suppose you are taking lithium chloride, which is sparingly soluble in water. When it is dissolved, any sparingly soluble substance will attain the saturation at an earlier stage. So when this is dissolved in water, it forms a saturated solution. From the saturated solution, lithium chloride dihydrate, this is called the water of crystallization. Already when I taught the practical, somebody asked the oxalic acid molecular weight becomes 126 when 2 molecules of waters are added. And I have already explained that it is because of the crystallization water. Here the lithium chloride also has 2 water molecules of crystallization. So immediately the lithium chloride dihydrate gets crystallized out from the aqueous solution, whereas the other substances do not get it crystallized. And moreover, lithium chloride dihydrate is a deliquescent salt. What is deliquescence? What is deliquescent? Anybody can answer. What is deliquescence? So the deliquescence opposite is efflorescent. Lithium chloride gets hydrolyzed in hot water, whereas other chlorides do not get hydrolyzed. Lithium nitrate, when it is heated, it liberates nitrogen dioxide and oxygen and forms lithium oxide, whereas other nitrates, they form nitrites and oxygen is liberated. And also lithium sulfate does not form alums, whereas other sulfates, sodium, potassium, potash alum is there, ferric alum is there, other alums are there, but it is not forming alums. And also it is not isomorphous with other. What is isomorphous? Isomorphism. What is isomorphism? These sulfates are not isomorphous with lithium sulfate, which means morphologically lithium sulfate is different from the other sulfates. Morphology, external appearance. Normally, the appearance has its own physical meaning. You know, suppose if you take a mango, the morphology is exactly similar to our heart. So mango is good for heart. Similarly, if you take the leaf of Vallarai, the Vallarai leaf morphology is similar to our brain. So Vallarai is good for our brain. So the vegetables, if you take bitter gourd morphology is similar to that of our pancreas. So it is good for the pancreas. If you take ginger morphology is similar to our intestine. So ginger is good for the intestine. If you take beans, its structure is similar to our kidney. It is good for the kidney. So look at the morphology of the vegetables and the morphology of our organs. Some similarity is there. And also the color. Suppose if you want to be mentally alert, eat all red colored fruits. If you want to be beautiful, eat all orange colored fruit. If you want to sleep well, eat all pink colored fruit. So the color and the behavior, morphology and the behavior, these are all having similarities. So lithium sulfate morphology is totally different from the morphology of other sulfates of the same group. So that is another anomalous behavior. Now, next behavior is high charge density and the high polarizing power. It polarizes even water molecule. See, water molecule itself is very stable, but even water molecule can be polarized by lithium ion. And because of this polarization, a lithium ion is found to be extensively hydrated. So normally degree of hydration will decrease when the size increases or when the charge density decreases. See, what is hydration? The solvent molecules will try to surround the ion because of the electrostatic attraction. This surrounding of the solvent molecule is in general known as a solvation. If water is the solvent, it is called hydration. If ammonia is the solvent, it is called ammonation. If a sulfur dioxide or something is a solvent, sulfonation. Something like this, hydration, ammonation. So hydration means simply the water molecules engulfing a particular ion. So because of the high charge density, lithium ion is extensively hydrated. As if you want to find out the size of the ion, you are finding out the size with its water of hydration. So the effective size is found to be larger. And the 18th point, because of the high polarizing power, it lowers the ionic character of its compounds. See, suppose if you take lithium iodide, lithium is the smallest, the top, an element which is found on the top of the alkali metals group. Iodine is at the bottom of halogens. So this is relatively very bigger in size. Lithium is smaller. Why we have taken a bigger anion? So that it is easily polarizable. Whereas lithium has a high polarizing power. When a high polarizing power and easily polarizable atoms combine, if lithium iodide is a purely ionic compound, then the dipole moment will be 11.5 d by. But when you measure it experimentally, it is only 3.25. There is a vast difference. It is because the partial overlap of the filled orbitals in the I minus with the empty orbital in the lithium plus. Already lithium plus has lost one electron from the s orbital, which is an empty orbital now. Whereas the iodine, it was having the s2p5 electronic configuration. Now one electron has come. So what happens? As the one electron has come, it becomes s2p6. So the completely filled orbitals and the empty orbital of lithium plus, they are getting a partial overlap. And because of this overlap, what happens? There is a small migration of a charge from I minus to lithium plus ion. So this reduces the dipole moment. That is why the dipole moment of the lithium iodide is found to be 3.25. Now, the 19th point. Lithium carbonate is thermally stable. Lithium carbonate is thermally less stable. If you heat lithium carbonate, immediately carbon dioxide will come out and the lithium oxide will be formed. Whereas other carbonates, sodium carbonate, potassium carbonate, rubidium carbonate, cesium carbonate are stable. And also, if you compare the lattice energy, lithium oxide lattice is more stable than lithium carbonate lattice. See, when you compare the lattice of other metals, carbonate lattice is more stable than oxide lattice. But for lithium alone, carbonate lattice is less stable than oxide lattice. So that is the main difference. Now listen. The next one is diagonal relationship. Diagonal relationship of lithium with magnesium. What is this diagonal relationship? The first element of a group having similar properties with the second element of the next higher group is called diagonal relationship. See, lithium having similar characteristics with magnesium, beryllium and aluminium having similar characteristics, boron and silicon having similar characteristics. These are all because of diagonal relationship. Now we are going to see this diagonal relationship is due to the similar polarizing power despite of the different charges, because lithium is +1 charge, magnesium will be found in +2 charge. So this is the diagonal relationship, the reason behind the diagonal relationship. Now I quit the meeting, please rejoin immediately.